Tonight we're going to talk about concavity. And before we start, I'm just going to introduce myself. My name is Sander Owens, and I am a junior in high school, so one of our student streamers here at Fiveable from Michigan. So, without further ado, so this is where you can find us on various social media. It's a great way to follow us and see what we're doing. And make sure when you're on your Fiveable page to select which subjects you're in, so you don't get emails about all of them, and so you actually pay attention to the ones that you get from the subject you're actually in instead of just deleting them. All right, so in the stream tonight, I obviously have just introduced myself, and I'm going to introduce the stream here. And what we're going to do first off is we're going to review these concepts of f prime, f double prime, just beginning with a very, very brief review of how you find them, and then kind of what they mean and what they can tell you. And then we're going to move on to concavity, which is the main concept from tonight, and that deals mostly with the second derivative of a function and what that can tell us about f. Then we'll move into two types of example problems. Now, on the AP exam, you're going to see questions about concavity and about first and second derivatives in general, asked in two categories. One is where you're going to give you a graph of a function, most of the time without a rule, since it'll be a piecewise function and a rule would be really complicated. And then they'll ask you where it satisfies certain conditions, and those conditions we'll get to later. And then the second type of problem that we'll look at are algebraic examples, where you're just given a rule and you're asked to find something about the function. Sometimes there may be graph matching, although we won't look at that tonight, but from the algebraic examples, it's purely manipulation of that equation and deriving to get what you want. And then I thought it would also be nice if we interpret these in the context of physics. So that is frequently in calculus. I'm not necessarily sure if this will show up on the AP exam, but I do know that in your classes, for instance, there will maybe questions using the terminology used in simple physics. So I'll quick go through how f prime and f double prime are interpreted in physics. All right, so without further ado, let's get started. So let's start by reviewing f prime, and f double prime by looking at how to find them. And remember, f double prime is just the derivative of f prime. There are no wrinkles for finding f prime. And so you'll see here I'm using what's called Lagrange notation, and that's what's commonly used in these problems. But if we have f of x, f prime is equivalent to dy dx. And then f double prime is d squared y dx squared in Lagrange notation. But on the AP exam, although you will see this Leibniz notation used elsewhere, they will generally use the Lagrange with the prime marks or the apostrophes with these problems, since just for typological reasons, because it makes a lot more sense. Okay, so I see, Jack, you just asked what's the difference between dy dx and d dx. Now, for all intents and purposes, you can probably treat them the same in terms of doing them, but generally dy dx will refer to a rule. So you'll often see, like, if I have f of x equal to 2x squared, you'll see dy dx will be 4x, and so that will be the general rule. Whereas d dx is what you're doing is more often used if you're finding it at a certain point. So if you wanted to find this at if we wanted to find the derivative of this function at, say, x equal to 2, we would say d dx of 2x squared, where x is equal to 2, and that would be 8. I think that's how it's used. Like I said, That's just something that I remember glossing over very briefly, but that's pretty sure how that's used. But for all intents and purposes on the EAP exam, that's really not an important thing. They generally will accept most derivative notations. So, but yeah, that's a very good question. So those notations really just refer to refer to a rule versus at a specific value. So like think f of x versus f of 2 in a different context. So now let's start remembering how to do derivatives. And at this point in the semester, I'm assuming you've probably studied derivatives. You've maybe even learned how to implicitly derive. I know some of my friends just had a test on that in school this week who are in calculus right now. But just a quick review of rules. The power rule is where if we've got x to the n, this is probably the first one you learned, it would be nx to the n minus 1. That's the basic power rule. Once again, constants just stay up front, they don't matter. For addition and subtraction, you split up into parts and then you add the parts together, and that will give you your end rule. If you've got f of x plus g of x, you derive that. You take f prime of x plus g prime of x. It's that simple. Product and quotient. The product rule, if you're having two functions multiplied together, it's the derivative of the easy way to kind of write it is fg prime plus gf prime. So, and you can do that in any order, or you can derive whichever function is cleaner and neater first. That's generally the way I do it. If whichever function looks neater out front, so for example, if f is a linear function and it'll just become a constant out front of g, which is maybe a trig function, then that's generally how I would do it, because as we remember from elementary school, multiplication or addition rather is of course commutative. Quotient is the one where you actually have to remember, so it's gf prime minus fg prime over g squared. And that one, once again, that's important. You do get the or to write, if you want that in words, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, which is pretty wordy, but if you just have that in your head as a cadence, like the quadratic formula, it really helps a lot. The next is the chain rule. If you've got f of g of x, the general rules, you can work from the outside in, so you're going to derive the outside with the middle part still in it, then you're going to multiply that by the derivative of the middle part, and that, like the name suggests, you can string as many together as you want for that. And then trig derivatives, you're probably just going to have, there's some mnemonics for how to remember them, but you're just probably going to have a set like on a review paper like this, where you'll have that list, and you just have to remember them. Exponential functions, the easy one is e to the x, derivative of that is e to the x. For anything else to the x power, you're going to multiply by your natural log of the base. And logarithms, similar thing, the derivative of the natural log is 1 over x. And then the derivative of log base b of x is the natural log of x over the natural log of the base. So that's just a really simple review of how to find your simple derivatives, which of course, that's something that you really need to have down pat. So I would recommend, if by this point you're still having any trouble learning how to derive, I would recommend, going through and just cranking out problems, picking any sort of function from your textbook and just working through those, or watching through, kind of mandatory plug here, or not mandatory plug, but a little plug here. If you have 5able Plus, you can go through and check. I've done a couple already, derivative practice streams, that you can go through and look and just nail them out until it becomes second nature. All right, so just a quick review. Let's find f prime and f double prime for these two functions. So you'll notice here that to find f prime of x, we've got a chain rule. And remember, this is kind of a wrinkle that we have with this notation for power functions, or for sine functions rather. So to notate a sine function, trig function raised to a power, you put it right there. So this is really 2 times sine of e to the x, of e to the x squared. So to derive this, we're going to start by taking the derivative of sine squared. So this 2 stays out in front, and it becomes 4. And the derivative of sine is cosine. So we're going to say 4 cosine, because the 2 multiplies out front, of e to the x. And then what we're going to do is see, you got to pay attention to that chain rule. I've caught myself making a classic error here. You can't just go along deriving and then not realize that you've double derived the chain rule. So what you actually need to do is you need to take that and keep that all together. So it's really 4 sine of e to the x times the derivative of sine of e to the x, which is cosine of e to the x, times the derivative of cosine of e to times the derivative of just what's inside here, which is, of course, e to the x. And then to find f double prime, of course, you would multiply all of that. You would do a massive product rule. And when you're doing product rules for things like this, what you've got to do is, once again, you've got to nest them. So you have to you break this up into 2 groups. It doesn't really matter how so you can do it like that or like that. But anyway, you're gonna have to do 2 product rules with a little thing in the middle. And and then for this one, it would be a similar process, except you do a product rule here. All right, so that's just a quick review of finding those derivatives. Now let's move into kind of the important part here, which is what these derivatives can tell you. So let's look first at what f prime can tell you based on a graph. So of course, because the derivative is the instantaneous rate of change of a function, if the derivative is increasing, if a function is increasing, therefore the derivative, or that instantaneous slope, will be positive as it moves tangent with the line. So if a function is increasing, its derivative will be positive. And if a function is decreasing, therefore its derivative will be negative. And if a function is stationary, its derivative will be 0, and that is the location of a possible extrema point. So just to kind of review what that means, I'll get to it later, but stationary, as if you recall, means if we've got the graph of a function and it does something like this, this is where it's stationary. So you can see where the slope here is 0. Stationary just means it's flat. And then possible extrema point, that means it's either a local max or a local min. So just to clarify that nomenclature there. All right, so let's look at what f prime can tell you given an example problem. So given we have this f prime rule, and we're going to say, what does the graph of f? Tell me all you can about the graph of f. And there are 2 ways to do this, as with many things. You can do this graphically, so looking at a graph of a function, or using something called a sine chart. So first, looking at this graphically, this is a graph of f prime of x. And now, if you're thinking about this logically, as I was when I first learned this, you probably thought, wait, can't you just find f? If you can derive, surely you can you can just anti-derive and find your rule for the function. The thing is, you can't remember because a lot of that stems to the fact that the derivative of a constant is 0. So there's always some numbers that you're not sure of, and so that will alter the graph of a function. So if we've got this graph of this function f prime of x, we're going to have to look for these points that tell us something about our function. So if we go back to our chart here, okay, so if we look, the most important thing is we're going to look for these points where the function is 0, because that's where we know that we've got stationary points, so we've got some possible maxima or minima. And so and then we've got this where it's decreasing. We've got this negative part here, and then it's positive here, negative here, positive here. So we can say so let's just first deal with negatives and positives. So when it's a negative, that means the function is, of course, decreasing. So we can say it's decreasing all the way up to this point, just about -3/2. It keeps, and then it increases. It decreases again for a short point, and then it increases. So now, and these extrema points, we'll get to how to determine whether they are maxima or minima later, although you can probably guess which way they are based on going from increasing to decreasing and such. So the other way to do this, is of course using something called a sine chart. So a sine chart is where we take these zeros and we is where we take the zeros that we know and we look at what the behavior of the graph is in between these. So I won't go through the trouble of actually calculating out what these zeros are, but you would say, well, the derivative is negative here, positive here, negative here again, and then positive here again. And the way you would do this is the algebraic method. So once you solve for the zeros, or you use the calculator, as we'll all do later, assuming this is on the calculator portion of the exam, you can just plug in values based on your graph in order to figure this out. And as with many things, you just have to figure out which one you're better and more consistent at. I was better at kind of using, I found that I was best using a combination of these two, often not making a formal sine chart, but using the table function on my calculator. So if we look at this, we can see that this adds f double prime, what f double prime can tell you. And you can see I've highlighted here this concave up and this concave down, since that's our focus here is on how do we know about this concavity. So you can see that if we've got something that looks similar to what we know about f and f prime, but here we've got it for f prime and f double prime, and this might make sense to you because of course f double prime is just the derivative of f prime. There's nothing special about it. And so that will be able to tell us this new layer of what happens when we have the function f. So we can see when f double prime is positive and the derivative is increasing, the function is concave down, or it's concave up rather. And when these two conditions are met, it's concave down. Then we have a possible inflection point. All right, so let's look at those inflections and those extrema points. So where a function is stationary is a possible extrema. And you may think, well, isn't when the derivative is 0, it has to be changing from positive to negative? Not necessarily. So something that is a stationary point but not a possible extrema would look like that. So you can see here the slope is 0, but it isn't a local max or a local min because it keeps going in that direction. It just takes a break, so to speak. And so a maximum will occur when the derivative of a function is 0 and it changes from positive to negative. And then a local minimum will occur where the derivative is 0 and it changes from negative to positive. So if we look at these graphs here, we've got f of x equals 1/2 x cubed minus 4x plus 1. So therefore our f prime of x will equal 3 times 1/2, which is 3/2 x squared minus 4. Over here, we'll have of that 5x. So what we have here is we've got a function, single derivative, and its double derivative. And so we've got these two stationary points, and we're going to see whether they're maxima or minima. So looking at our first derivative, we can see that those are those corresponding points. Those are those zeros. And you can see that here, if we just had this row, we can see it's changing from positive to negative, and we can see that it is indeed a local maximum. Oh, we got another question here. You're right. F double prime should be 3x. Sorry about that. I don't know what I was thinking there. Yeah, wow, that was a weird brain glitch there. Sorry about that. So f prime is indeed 3x, and you can see that actually is indeed what I've graphed there. I think that was just an error carried on from somewhere in the back of my brain. So anyway, so we can see here that we've got a minimum because we can see the derivative is changing from negative to positive. So you can start to see where this is going with your AP problems, where they'll give you a graph of a derivative, or they're giving you a rule for a derivative, and it'll ask you whether it's a maximum or a minimum. And of course, the only way to know that is to do the test, because given this, you have no idea what figuring out this was, because you have no idea what this +1 would be, since it just disappears in the derivative. All right, so now let's look more at concavity. Now, what is concavity? Or rather, to talk about concavity, we got to first talk about inflection. So we'll come back to inflection. What is an inflection point? Inflection, well, that's when the double derivative is 0. And you might be wondering, well, what does that tell us? And those inflection points measure a change in concavity. So, and that brings us to our next point, what is concavity? Well, concavity, it measures whether the rate of change of a function's derivative is increasing or is decreasing. And you might be thinking, well, rate of change, that is a signal word for a derivative. And you'd be correct in that regard. So we're basically measuring whether the second derivative is increasing or decreasing. And so you may have heard you may have heard concave. It's often paired with the word convex. In fields like physics and optics and such, but here we don't call functions concave and convex. We call them concave up and concave down. Although I suppose you could call them convex down and convex up, but nobody does that. Just concave, you always describe them with concave up or down, not with convex for whatever reason. Unless you're a bit of a snarky high school student trying to confuse the teacher by being annoying but technically right, as a friend of mine once was. Anyway, so if f prime is increasing or the double derivative is positive, then the function is concave up. And so we can see, if we delineate our points of inflection here, where it's going to change, we can see that concave up would be this section here and this section here. And we often say it looks like a cup or a spoon. And then if our single derivative is decreasing and therefore our double derivative is negative, then the function is concave down. So that would be in these points over here. And you'll see that alternately described as a cap or an umbrella. And if you are like me and you don't really like the silly mnemonics, you can just memorize it by up and down are the way it opens, so not where the top is. So if it's concave up, it opens up, and if it's concave down, it's opening down. All right, so now using this concavity, this allows us to save a step from our maxima and our minima calculations by doing something called the second derivative test. And using this second derivative, this gives you a much better way to see if these functions are maxima or minima. Now, why is this? So if we think about a function, let's just take a really simple cubic function, since those contain a concave down and a concave up moment. And we've got these 2 points. Whoop, accidentally tabbed out there. And we want to see if these are maxima or minima, just based on what we know. A really quick way to do it. So if you think about it, well, rather than the whole changing from negative to positive business, because if you're just given a function rule and you can't graph it, you have to think about, you've got to check 2 points. But here, this allows you to check just one value without having to plug in 2 values. And the reason this works is if you think about how a maximum is, it always has to be from where the derivative is changing like this. So by nature, it has to be on a portion of a function that is concave down. And vice versa, if it's a minimum, then it has to be on a portion of a function that is concave up. So using that fact, you might be able to reason that, if your double derivative is less than 0, that if we've got these stationary points and our double derivative is less than 0, i.e. it's concave down, then it must be a maximum. So revisiting our problem from earlier here, we can see that, checking this and this, we don't have to look. If we just had this rule, we can see, at this point here, our double derivative is negative. It's less than 0, so therefore this point must be a maximum. And we can look here, and if we see it's greater than 0, then it must be, and if we look at this other point, we can see that it must be a minimum, and it's therefore concave up. All right. So this is probably one of the most useful things for concavity, because it means you only have to enter one value of a function into a function rather than checking on either side of a point. So now let's look at some examples. So here we can use that table that I showed earlier to figure out when these conditions will be met. So these questions are of the graphical type. We can see, so we're given this function, no rule, and we have to and we're asked when is f prime less than 0 and f double prime also less than 0. Well, if we go back to see when's f prime less than 0? Well, if we go back to our first table, we can see that when f prime is less than 0 or negative, the function has to be decreasing. So this means it must be decreasing. And f double prime is less than 0. Now, when f double prime is less than 0, it's negative. That means it has to be concave down. So if we take this inflection point, let's first rule out a concave down. So it means we can rule out this entire portion of the graph here. And then, so that satisfies this condition. Now let's look, when is the derivative less than 0? So when is the function decreasing? And therefore, so the correct answer would be something that looks like this, or whatever this value of the function is. And the important thing to look at here is that for AP multiple choice questions, if you have not taken an AP mathematics class before, every multiple choice question will have 5 answers. And generally what it'll look like is you'll have one oddball answer maybe, and then if they like to do these 2-part conditions. So when is this true and when is this true? And generally, if you look, it'll be about half and half for each of the conditions, and you've got to find the one that has both, and every answer will have some sort of logical sense. So the way to do these is, of course, you go through by condition. So you would start with saying, okay, when is f prime less than 0? And that means the function is decreasing. So you rule out all the ones that contain where the function is increasing. And of course, because of the nature of an AP exam, there will never be a select all that apply. And that is, of course, very helpful because it means you can just strike out ones that you know are not correct. And then you go through, and of those, you pare it down to the ones that satisfy the second condition. And of course, process of elimination is always going to be your friend with this sort of thing. All right, so moving on to this second example problem, when is f prime greater than 0 and f double prime also greater than 0? So f prime is greater than 0 if you look at the chart that you have. If you look at a chart, or if you look at a little chart that we made earlier, or you just know, okay, the derivative is greater than 0, which means the slope has to be positive, which means the function is increasing. And when it's f double prime greater than 0, that means that the derivative has to be increasing, which means that the function must be a concave up. So like that. And so just first checking through our increasing sections, that rules out all of that, and it's concave up, and this function is actually entirely concave up. So it's from this point, which looks to be right about negative 1.5. So it would be, oh, that's a really bad infinity, sorry. So this would be it. Now, what if I change the problem? And what if I said, okay, when is f prime less than 0? Now, this would be another example of when you can use your AP reasoning skills that you've learned, and you can look and you can say, okay, once you've figured out what each of these mean, you can see it is never, this function is never concave down, because you can notice here we've got this point which looks kind of like, which could be an inflection point, but you can see it just keeps going up afterwards. So it is entirely concave up. So you can see, oh, it must be E, none of these. And so that'll be your frequent answer. Always look for the easy way out. Always see if there is one, if there's something that you know it immediately doesn't exist, or it's 0, or whatever. That's another nice AP tip that you can use. All right, so let's look at this new graph. And so this is a function of a hypothetical f of x. And this question asks us, where is the double derivative 0, and where are any inflection points? And so this is kind of a loaded question here, because you can see, you might think, well, if you look at a chart that you scribble down on your paper, and I keep talking about this chart, the one I showed you earlier, I'll show you the one that I always scribbled down just to make sure you've got a possible thing. But remember that when you abbreviate things on your chart, there will always be little like asterisks that you should always have in your mind when you look at these. So you can see f double prime is 0 when we've got these possible inflection points. But so we can see that if we got this function here, the double derivative of 0 would be where we've got inflection points. So right here, but you can see this is all concave up, but the double derivative would most likely be 0 here, because you can see we got the stationary point, so therefore f prime will be 0, and therefore f double prime will be 0. We've got another one there where it changes from concave up, but you can see of those 3 points, only these 2 will be your inflection points. And that's what I mean when I say you've always got to remember that f double prime has to be not only 0, but it also has to change sign. And the same goes for stationary points with possible extrema points. So even if the value of a derivative will be 0, it not only has to be 0, but the values also have to change sign. So that's another really important caveat to remember for your little rules. All right, now let's say, oh, this is no longer the graph, but this will be the graph of f double prime. And this is a frequent formula that they'll use on your free response questions. Are the straight lines, Lexi asks, are the straight lines both concave up and concave down? Now, I'm assuming you're referring to here, and it really has to do with what the behavior is outside of it. So you can see from here, if we mark those inflection points again, it has to do with kind of the overall shape. So you can't just look, you've got to see what the general trend is from here. So you can see here, it's got that characteristic hump-like shape. So it doesn't have to be a curve to be concave. So you can see all through here, it's concave up, or rather concave down, because from here to here, the double derivative would be positive, if that makes sense. So the straight lines, it has to do with, it doesn't have to be curved for concavity to apply. So I hope that answers your question there. So you got to look at the overall shape. And so, but if you had a straight line, you would say, well, is that line concave up or concave down? And if you think about it, that's a special case because this would have a function of the form f of x equals ax. And if you derive that, or mx, if you want to use the convention for slope, so then f prime of x would just be m, and then f double prime would just be 0. So you can see that for a pure straight line, the second derivative is really kind of irrelevant. And so you'll never have to worry about that case. But yeah, to answer your question, straight lines will have concavity. They're not simultaneous. You just have to look at where it goes after that straight line. And of course, remember where your derivatives are undefined at kinks or angles in the graph or at jumps. All right, so going back to our initial question here, if this graph were f double prime of x, where would the derivative be increasing? So an easy way to think about this is anytime you've got f double prime and f prime, remember that the relationship between those two is the same as the relationship between f and f prime. So if f, we can see that if it's increasing, decreasing, or stationary, the derivative is positive, negative, and 0, respectively. And so that also applies to these two. So f, where is f prime increasing? Well, that would be where this would be positive. So from here to here, f prime would be increasing if we're assuming that this is the graph of f double prime. All right, so now let's move on to some algebraic examples. So this is more of the form that will be more prevalent, probably in your multiple choice questions where you just have to quick fire, and often in the calculator section. So when it says algebraic, that doesn't mean that you have to do these longhand. It just means that you have to know how to do these. You have to be able to do these very quickly, since the key on the generally most people find that on the calculus multiple choice questions, it's not like they've got tons of time, they feel, but it's not like they're rushed. So if you take your time and you work through these, whichever method you find most efficient, you'll probably be fine. Those graphical ones will be more often on a free response question, as I was saying before I answered Lexi's question, where it'll give you a graph and then you'll ask questions, say, assume this is f, when would these conditions apply? And another type of question that I just remembered as I was streaming here now was where you've got three functions and you're asked which is f prime, and which is f double prime. And of course, they'll never give you ones that are simple where you can recognize as cubic, quadratic, linear. But if I were to go back through my slides to a problem like that, here is how you might figure that sort of problem out, because I guarantee that if you do not see one on the AP exam, a question like this on the AP exam, you probably will see it in some sort of exam in class if your teacher uses any sort of AP material. So the way to look for that is to remember the relationships and just look for these key points. So you're going to look for these stationary points. So if we were seeing which one, we can just pick one and see, oh, if we were to pick this one, I'm going to say, oh, this one is this one is 0 here and here. So the thing that derives to get this must have a maximum and a minimum there. And of course, this is all made easier by the fact that they're all superimposed on each other. So you might have something like this, and then they'll be labeled Roman numeral 1, Roman numeral 2, Roman numeral 3, and it'll say which one is which. And then it'll either give you options or have you identify. So the way to do that, like I said, is just to check for those critical values and those relationships you know. So for example, look for one that has an inflection point and then see which function is 0 at that same point. So if we had this a bit messy, you can see we got an inflection point here, we can see this one is 0. So we know that that must be the derivative, and then you check other points until you know you're absolutely sure of that one. Like I said, those ones are complicated, but I would guarantee you that they're fairly prevalent. All right, so back to our algebraic examples. So when is this function concave up? So this function is concave up when the double derivative is positive. So let's find that double derivative. So f prime will be squared plus 6x plus 5. So f double prime will be 12x plus 6. And now, at this point, this one's fairly easy, so I'll do this one completely algebraically, not using my calculator. So if I were to solve for 0 to find our our zeros, we can say that, oh, our 0 is at x equals to negative 1/2. So at negative 1/2, we'll have something looking like this because it's a positive slope. And this is just, obviously, this is a simple one because it boils down to a line. And looking at how to graph a line, that's a fairly simple task. And so you might know how to do that, but as we'll see for later ones, it really makes much more sense to just plug it into your graphing calculator. As the AP Calc exam is, if you're just doing multiple choice, don't try and exercise your algebraic prowess, as it were, to figure this out. You can just use the most effective method possible. So we can see that knowing that a function is concave up when the double derivative is positive, so we can see, oh, it's positive from here onward, and it's changing sign. So it would be from negative 1/2 to infinity. So that's how you would do number 1. Now this next one we can see, when is f of x equal to sine x concave down when we're looking at between negative 2 pi and 2 pi. So basically within one period of the graph. So using our knowledge of trig derivatives, let's find the double derivative of sine. So f prime of x, the derivative of sine is cosine. And if we do the double derivative of that, we will get negative sine of x. And this is a rather interesting property of trigonometric functions, is that if you were to keep deriving this at f quadruple prime, you will get back to f of x equals sine x. And so you'll actually end up using this later in calculus, probably in your second semester when you're learning more about integrals. You'll do some interesting problems using this property that not only are the functions periodic, the derivatives are periodic, as it were. So you'll keep deriving and you eventually get back to itself. So for this one, I'm just going to use my TI-84 calculator, and because it's way easier to just let the calculator solve it. So if I input negative sine x and I go to a table and I make my increment 0.5 pi, we'll look at where it changes sign between negative 2 pi and pi. Quick plot this here in another tab, negative sine x, and if you were look at it, you can see, oh, well, the inflection points for a sine graph are, of course, at 0 where it crosses the x-axis, because if you think about the way a sine graph looks, because a sine graph, of course, looks like this, you can see that you'll have inflection points every time here. So it will be concave down. If we're looking at negative 2 pi, right between negative pi and 0, and between pi and 2 pi. And sorry, if I had planned this better, I would have used the TI-84 program, but I unfortunately do not have that ready. So that will not be possible. But once again, for this, you would just look at your calculator and you would see, oh, this is where it's concave down. So it'd be concave down on our graph here, from here to here, and from here to here. All right, so Let's move on. Just looking at time here, I'm actually going to skip a few problems to this number 6 here, because this is to this number 5 here. This is an interesting problem. So when is f of x given that f prime is equal to 2x squared plus 5x concave up? You may be saying, oh, this is, you might be kind of worried here because we can see, oh, we don't know what f of x is, and so we can't. But remember, using our relationship between f prime and f double prime, we know that concave up will occur when the first derivative is increasing, and therefore when f double prime is positive. So we can just go about this as we normally would, deriving that. So f double prime will be equal to 4x plus 5. And then solving that to find our 0, see that x will be equal to negative 5 over 4. So if we graph again, we'll have that point. Because it's a positive slope, it'll be looking like this. So it will be concave up from negative 5 over 4 all the way out to infinity. And so that is that would be how you would do this problem. And on a similar vein, let's look at number 6. So when is f of x equal to x squared plus 5 concave down? And this is another kind of special case here. So you might be saying, well, you might be predicting what's going to happen. So if we do the first derivative is equal to 2x, and then the second derivative is equal to 0. So if you think about that, and then if you think about what the graph of this looks like, you can think, well, if you think about this x squared plus 5 parabola, this one will in fact never be concave down. So that's another way to look at it. If you've got a parabola and I ask whether it's concave or concave down, you just need to look at your leading coefficient here for the answer, because parabolas never have points of inflection. They're either always concave up or always concave down. And so therefore, if that first is positive and it opens up, therefore it'll always be concave up. And if it's negative, so therefore it will be concave down. Now for our final task here, we're going to interpret these in the context of physics. So this is not something that you'll be directly asked on the AP exam, but this is good knowledge to have for word problems in your calculus class. Looking at this, we can see that the basic function in any sort of physics that you might do calculations with these involving motion is your position function, x of t. Now, in the context of motion, your derivative is, if we got x of t, you're saying what is the instant rate of change with respect to time. So if we think about slope as rise over 1, we're saying change in position or distance over change in time. And that is, of course, velocity. So the rate of change of your position is your velocity. And that, if you think that makes a certain logic to it. Now let's think about what the derivative of that rate of change is. So x double prime of t. So what's your change in velocity with respect to your change in time? So if I'm going faster and if I'm moving at a speed and my rate of change of that is changing, that is going to be, well, when you're moving between two velocities, that would be your acceleration. So the derivative of your acceleration is something is of course your acceleration. And you can keep going of this, although you really won't go this between your advanced physics. The derivative of acceleration is called jerk, and the derivative of jerk is called jounce. So you might see this, but you probably won't go that far. But this is just something to know because this will make your physics a lot easier, and you'll see a lot of word problems like this in calculus. So if we've got this graph of of position, when is your acceleration positive? And so your acceleration, so this would be f and then your acceleration will be f double prime. So when is your rate of change of acceleration? So when is your acceleration positive? Well, and of course, when is any derivative positive? Or when is any second derivative positive? That is, of course, when the function is concave up. So if we look at our inflection points from this function from earlier, we can see that here it is concave up. So therefore, this is where acceleration is positive. Now let's suppose for a moment that once again, this is your position function, but in this case, when is your velocity increasing? So if we look, when is your velocity increasing? That is, of course, the first derivative. So that is when that is also when it's concave up. So that will be true at the same time. So let's look at the third case. When is acceleration decreasing? Or rather, when is acceleration negative? So you're decelerating. And when is velocity positive? So velocity will be positive when the function is increasing. So velocity will be positive. So we can rule out this portion. But then when is your acceleration decreasing? So your acceleration is negative when your function is concave down. So that means all through here, this will be increasing at a decreasing rate. So it'll be true for here and then for here. Now, more than once so this is that in the context of physics, and I hope this will prove to be helpful when you do that sort of problem. Now, moving along, you may have heard me talking about this table that you have. And this is the easy way that you can use to remember how functions work. Now, the relations between your function, your first derivative, and your second derivative. So, what you're going to do, so the easy way to start is with this table. So you can always remember that when you start by saying increasing, decreasing, stationary. And then you say, well, when a function is increasing, its slope is positive, so therefore the derivative will be positive. When the function is decreasing, its slope will be negative, and therefore your derivative will be negative. And when a function is stationary, we got a possible extrema. Our derivative will be 0, and we can copy that relation from here up to here, because we know that the relationship between f and f prime is the same as the relationship between f prime and f double prime. And then you just have to add in this little box for concavity. Of course, as I've said a bunch, always remember that these are huge asterisks. You always remember that in these, your derivative in question needs to also be changing sign in order for there to be an extrema point or an inflection point. And always remember that the second derivative test will enable you to check for those extrema a lot faster. Because concave up, because if a function is concave up, it will be a minimum, and if a function is concave down, it will be a maximum. So that's all I have for tonight. I've already answered some questions, so I don't think there will be any more here. And just any other, I like to always end my streams with some brief advice for AP exam. I've already dropped that in, some of it with relation to the topic at hand, in this case, concavity. And I would really recommend that table is something I would say memorize, because on the AP exam, this is something that when you get flustered, one of the first things that happens is things jumble together. So I would recommend having that table written down, even if it's just literally INC DEC stat, and then UN and inflection. So just however you, but just remember that this is something that's really, it's really, once you get it down like derivatives, it just becomes kind of a simple process. And once you do this a bunch of times, it will become really kind of second nature. So don't worry, it confused the heck out of me the first time I tried this. But eventually, yeah, just remembered you got to use that table and always check for your changes in Sine. And then when you're making those sine charts really help you. Oftentimes, some of those pedagogical tools that your teacher will use, those charts are just kind of training wheels. But here, I would recommend keeping them on, making your sine charts for when you need them, and then doing that to help you delineate them when you have to do it completely algebraically, if this is on the no calculator section. Although generally, those problems of the graphing type will be more on the non-calculator, and then the algebraic will be on the calculator. So they are polite to you in that regard. All right. So this is once again where you can follow us on social media to get updates for all of the things that are happening on our platforms or on this platform. And I hope you have a great week and that you have a good Thanksgiving. And thank you for stopping by here and being the responsible student to review some things from your class. I hope you do well on the AP exam. I know since you're here, you probably will. So thank you all and have a great night.